I'm Aditya Vichare, and I would like to present the things you can do and see in the quantum world, my excursions in this field, and most importantly, to utilize your curiosity effectively. Today's talk is majorly going to be about the means by which you can enkindle scientific inquiry, ask the right questions, find the best answers, and most importantly, to build this recursion of asking questions and getting answers till there are no solutions left. Well, that's when you theorize the answers yourself. Now that's called being a scientist. I choose quantum mechanics as a guideline or an example to this approach, because there are not many questions you can ask in quantum mechanics before the answers start running out. Now, if any one of you delve further into the topics that I introduce you to in this talk, you would notice some of the terms that I use in this talk deliberately. And there's that instant connection. Oh, I've heard of this before in this talk. Ever since childhood, I've always started exploring things in science and math through books, online videos, asking my relatives who are experts, etc. It is perhaps imperative for a curious person to do this. Now, everybody isn't born curious, but every video that he watches, every book that he reads, every little thing that he explores acts as a catalyst. And the rate-determining step in this chain reaction is that he gets puzzled by a question or a thought. I credit this approach for my performance in the Indian Olympiad qualifier in junior science. I reached the orientation cum selection camp at the Homi Bhabha Center for Science Education at Mankurd, near the atomic reactors at Trombay. Only 35 students from all over the country until grade 10 are eligible for this. Sir Isaac Newton has rightly said that if I have seen any further, it is because I have stood upon the shoulders of giants. Modern science stands upon the four basic pillars of classical mechanics, quantum mechanics, special relativity, and quantum field theory. Now I exclude special relativity and quantum field theory because they require specialized equipment to do experiments with. But why quantum mechanics? Well, this is because it requires careful research in this field. Quantum mechanics serves as the basis of making nanometer-long transistors. That's about the size of a glucose molecule. And spoiler alert, there's going to be a brand new and fascinating side of glucose that you'll see in this talk today. Also, it serves as the basis of exploring quantum fluctuations that have created the universe and may even cause its death. Note that in this talk, I will introduce you to a lot of topics very briefly. Each little topic that I introduce you to could easily be a series of lectures, tens of hours long. Basically, I'm going to take you to a huge pool of information. But I wouldn't be so harsh as to push you right into uncharted waters. I urge you to wear the safety jacket of curiosity and personal interest as you join me. Beginning early. The general interpretation of quantum mechanics by the people today is based loosely off of the wildest theories and paradoxes. Images like these pop up in our minds when you hear about it. Any Marvel fans over here? Okay, more than I expected. This image should be recognizable to you. This is from a movie that's related to quantum mechanics, released last year. Now, is quantum mechanics really something like that? No, it isn't. Allow me to explain with an example that's cheap and easy to get our hands upon. How about lasers? Have you ever stopped and wondered how lasers really work? Lasers are the direct result of the quantum nature of photons, discrete light particles. I was really fascinated when I first learned about this. It is so fascinating to notice that something that we took so much for granted could teach us about the fundamentals of the universe. Notice how the question, how do lasers really work, seems unrelated to quantum mechanics. But that's how you are leveraged to learn more about it. Now you might say that asking the right questions is a really hard thing to do. But notice that the more questions you ask, the more likely you are to find something truly great. Talking about probability, quantum mechanics is driven by probability. In fact, Albert Einstein did not really like this idea that quantum mechanics is driven by probability, and he famously quoted, "God does not play dice." However, probability serves as the basis of modeling atoms and every quantum system today. In fact, every chemical reaction is a game of chance. In engines, in factories, even in your body, every metabolic process just happens to occur as the right molecule finds its way to the right enzyme. In fact, it finds its way to the right part of the enzyme. And that's when just one of thousands of reactions needed for a single metabolic process occurs. Isn't it fascinating to see how our bodies function and replicate with this model of molecules blindly striking into each other? Can you imagine DNA being replicated immaculately and without any single error, just by amino acids bumping into each other? Well, you might ask, where's quantum physics in this? Allow me to contradict myself as I show with that very same laser that light isn't just a particle, but a wave as well. In fact, it's a wave of probability. It's a wave of where light is most likely to go. This is the double slit experiment. If you shine a laser through two slits, if it were a particle, you'd expect to see two slits as the image, but you don't. And that is because light is a wave. You can see similar things with a CD and a phone screen as well. Keeping it with the theme, of course you can try this at home yourself. You just need a bit of a laser and a bit of cardboard with two slits in it. Can you even imagine that you just deducted the quantum nature of light, its realities, the fact that it's a wave with just a laser and a piece of cardboard? But fundamental questions arise that is light really a particle or a wave? Well, answers to that are yet to be found. So are we really getting anywhere? Stuck? Perhaps not. When the fundamentals get hazy, we digress and ask related questions. We get those answers, connect the dots, and figure out a new theory. In order to prove the applications of quantum mechanics, allow me to digress into medicine. This is ibuprofen, a well-known painkiller. But just the mirror image of that molecule is absolutely inactive. How does taking a mirror image of a molecule have such drastic effects? Here's another example. The smells, the chemical that causes the smells of oranges and lemons are mirror images respectively. But why does this occur? Well, this is because of optical activity. Some molecules in nature can rotate light. Look, here's some table sugar rotating light. You can do this experiment at home. You just need a light source, such as a mobile phone that I've used, and a glass of sugar water. You will need quite a bit of sugar for this. Just 2 tablespoons won't suffice. The glass at the bottom is the sugar glass, and the one at the top is just plain water. Notice how sugar can rotate light, creating colors from blue to orange and back to blue again. The sunglasses that I've used at the top are the polarizing filters. Note that you will have to use polarizing sunglasses for this experiment. So why does this occur? Well, light is an electromagnetic wave. For those of you who pay attention to the details, light consists of an electric wave. Well, I'm being loose on the terms right now. An electric wave that goes like this. But a magnetic wave is also associated with it that goes perpendicular to it. In the diagram shown, I've only shown one of them. Either the electric one or the magnetic one. Doesn't really matter. Well, Notice how you can write 2 plus 2 as 4 and 4 as 2 plus 2. We are going to do the same thing but with waves. We're going to add waves together. Something called superposition, just another fancy term. Notice that, let's just consider that the wave travels this way, towards me. So I point the thumb towards me. Notice how I've raised up my right hand. And I curl the fingers of my right hand. And as I move my fingers along the direction of the thumb, notice that this kind of pattern is made by the red wave. I can do the same thing with my left hand. I take the thumb in the direction of propagation, curl my fingers around, and travel in the direction of the thumb. That kind of motion is exhibited by the blue wave. So I can call the red wave as the right-handed polarized wave and the blue one as the left-handed polarized wave. Now check out what happens when I add these two. You get the yellow wave. Notice that the yellow wave is a plane wave. It just travels in a single plane. It's not some fancy helices, it's just a sine wave. Now, when I said 2 plus 2 is 4, but I can also represent 4 as 2 plus 2. So I can very easily represent the yellow wave as the blue and the red one. We are going to exploit this to explain why sugar rotates light. The way sugar molecules are is that they selectively slow down either the red or the blue wave. See what happens when I shift the blue wave, that is, slow it down. The yellow wave rotates. That is optical rotation. That is what you were seeing in the image. Now you might say that the colors were changing as well. Well, that's because different colors rotate by different amounts. So if I have a red wave, and the filter, that is my sunglasses, were in this orientation, and the red wave was in this orientation, the red wave passes through. You see red light. But if, let's just say, at that very instant, green light was rotated this much, it wasn't passing through. You weren't seeing the green light. So that's optical rotation, and such special molecules in nature are called chiral molecules. Methods to learn. Now, there's tons of misconceptions about quantum mechanics and science in general. I hope to imbibe experimentation, doing things yourself as a part of learning. Knowledge isn't just limited to the textbook. The day and age we live in today is feeding us with an endless stream of information. And we just view it and forget it, perhaps just a few seconds later. This endless stream of viewing and forgetting gives us no worthy knowledge, and we're simply wasting our time. The widespread misconceptions about quantum mechanics is perhaps due to the way pop culture presents them. Of course, Marvel fans can relate to it, the kind of things you have to do to get to the quantum world, open portals and everything. But I took you to the quantum world. You just saw the highlights of the quantum world through a laser, a bit of sugar, a CD, a DVD. In fact, you are holding the quantum world in your hand right now. There's millions of processes going inside your digital devices that are determined by quantum mechanical processes. Millions of them every second. You are holding the quantum world in your hand. What we lack today is the will to stop and question the information that we gain through our screens. We have developed what should just be a fraction of our lives into a separate reality of its own. Curiosity is psychologically hardwired into our brains. We are built to notice patterns. This is how medieval man interpreted a warrior with a sword and a shield. Can you notice the warrior? The best I can see is 3 stars are collinear, and I can see 2 trapeziums. Can you have ever imagined that this could have been a warrior? Medieval man also interpreted this bunch of stars as a queen holding a mirror. The best I can see is a W. Well, Here's the Queen. Today, our imagination is engulfed by others' interpretations. We have been blinded by the realities that are presented to us. It is seldom that we think about the world around us, above us, and maybe even below us, than the world behind our screens. Yes, screens do have the potential to teach, but learning arises from reflection and not just reading. Reflections. Quantum mechanics is crucial in today's world, as it is the very basis behind the working of nanometer-long transistors in our digital devices, the tools of determining the birth and the death of the universe. In fact, it also serves as the best example to do astrophysical calculations as well. However, quantum mechanics has gained infamy. We have developed the wrong notion about quantum mechanics in our lives. Well, this talk not only gives an incentive for us to explore quantum mechanics, but also allows us to notice that there are faults in our modern-day communications. Quantum mechanics has allowed us to overcome several problems, such as our computing speeds through quantum computing, computers that are millions of times faster than the best computers that we have today. It could drive revolutions in nuclear energy. And believe it or not, nuclear energy is the safest means of energy production. Well, this is yet another example of miscommunication. Have you ever imagined how many deaths have coal and petroleum caused? All we hear about is Chernobyl and Fukushima Daiichi about nuclear energy being a disaster all the time. Well, quantum mechanics has also allowed us to calculate the curvature of space-time. This thing can determine the fate of the universe. It can determine if the universe is going to collapse in on itself, expand out, or just cause heat death. I know it sounds miserable, but don't worry about it. It isn't going to happen in our lifetimes. Erwin Schrödinger has rightly said, the task is not to see what has never been seen before, but to think what has never been thought about what you see every day. Thank you.